Everyone, I'm going to talk about the evolution of Bloom filters from the original classic design to later variants that improved their theory and practical use. Bloom filter is a compact probabilistic data structure used for set membership queries, meaning questions like, is this element in the set or not? It uses two main things, a bit array of size m, where all bits start at 0, and k-hash functions. To insert an element, we hash that element using all k-hash functions, and each hash function gives one position in the bit array. We then set these positions to 1. To look up an element, we hash it again with the same k-hash functions and check those positions. If any one of those are 0, then the element is definitely not in the set. If all of them are 1, then the filter says the element is probably in the set. So Bloom filters never gives false negatives, but they can give false positive. See how insertion works. Suppose we want to insert the element x into the Bloom filter where k equals 3. We compute the three hash functions of x, and those hash functions give us three positions in the bit array. We then set those three positions to 1. The filter does not store the element x itself. It only stores the information that these particular bit positions are now set to 1. This is what makes Bloom filters space efficient. Look at how membership queries work. Suppose we want to query an element y that is not actually in the set. We compute the same three hash functions for y and then check the corresponding positions in the bit array. This is where false positives come from. Those bits may have been set to 1 not by y, but by other elements that were inserted earlier, such as this bit and this bit were set by x. So a Bloom filter can incorrectly return a positive result for an element that is not actually in the set. This is what we mean by false positive. It never gives a false negative because if even one required bit is 0, then that element definitely was not inserted. Suppose we inserted x and y from the previous examples. If we want to delete y, we need to set its corresponding bit positions back to 0. But the problem is that some of those bits position is used by x. So if we clear those bits, we may accidentally remove another element. This is why a standard Bloom filter does not support deletion, because multiple elements can overlap on the same bits. Clearing a bit is unsafe. These examples, we can see why the original Bloom filter is limited. First, false positive can occur. This means that filter may say an element is in the set when it is actually not. Second, deletion is not supported because multiple elements can share the same bit positions. Third is performance of a Bloom filter depends heavily on choosing good parameters, especially the size of the bit array and the number of hash functions. Modern applications need better space and lookup performance and support for more dynamic operations. These limitations are what motivated researchers to improve both the analysis of the Bloom filters and the design of new variants. Most important theoretical questions about Bloom filter is their false positive rate. For many years, a classical approximation was used for the false positive rate. However, in 2008, Bosch and his co-authors showed that the standard deviation was flawed. The issue was that it assumed independence in a situation where the assumption does not actually hold. In 2010, Christensen and his co-authors corrected that analysis and gave a correct formula. More recently, in 2023, Fan and his co-authors proposed an information-based approach for finding the optimal number of hash functions without relying directly on false positive formula. So this is an important part of the Bloom filter story. Even though the data structure itself is old, our understanding of its behavior continued to evolve for decades. Our main result is that the classical formula is not exact, but it is still often a good approximation when the filter is large enough. For smaller filters, the difference can matter more, so the corrected analysis became more important. Another key takeaway is that choosing the right number of hash functions k is critical. If k is too small, the filter may not use space efficiently. If k is too large, too many bits get set, which can increase the false positive rate. So later work did not just correct the mathematical detail, it helped us understand when the classical approximation is acceptable, when it is not, and how Bloom filters should configure more carefully in practice. Because of this limitations of the standard Bloom filter, several variants were developed to improve its practical use. One important variant is the counting Bloom filter. Instead of storing just bits, it stores small counters. This allows deletion because we can decrement counters instead of simply clearing bits. Another variant is the complement Bloom filter. It adds a second Bloom filter built on the complement set, and this helps identify some true positives more reliably, reducing unnecessary exact lookups. The third is the cuckoo filter. It also supports deletion, offers very strong lookup performance, and in many practical cases can be more space efficient than a standard Bloom filter. Counting Bloom filter works like a standard Bloom filter, but instead of a bit array, it uses an array of small counters. Instead of setting the corresponding positions to 1, we increment the counters at those positions. In this example, we see the value corresponding to y is set to 1. We insert y. To insert y, we simply increment that position to 2. Now, if we want to delete y, we hash y again and decrement the counters at its corresponding positions. This is why counting Bloom filters support deletion safely. Of course, the trade-off is that counters use more space than a simple bit array. Next is the complement Bloom filter. The idea here is to use two Bloom filters instead of just one. The first Bloom filter is built for the actual set S. Um, and the second Bloom filter is built for the complement set as complement, meaning all the elements not in S. Now consider a query. If the original Bloom filter says positive, but the complement Bloom filter says negative, then we can conclude that the element must truly belong to the original set. Why? Because Bloom filters never produce false negatives. So if the complement Bloom filter says the element is not in the corresponding set, then it really is not there. That means it must be in the actual set. That, this helps identify some true positives directly without needing an additional lookup. Now let's look at how complement Bloom filter identifies true positives in a high-level example. Suppose you have a universe A to F, and A and B are in your set, and the set complement would be everything except A and B. Now, if you want to query A, the original Bloom filter would return positive because A is in the set, and the complement Bloom filter would return negative. The conclusion we derive is that A is definitely in the set. In the next example, if you want to query C, the original Bloom filter returns positive because of false positive, and the complement Bloom filter uh, says it positive. The conclusion is that you cannot tell which Bloom filter is wrong, if any. So the uncertainty still remains. To conclude, Bloom filters are powerful because they trade exactness for space efficiency. The original Bloom filter is simple, fast, and very memory efficient, which is why it became so widely used. But as we saw, it also has some important limitations. Over time, researchers improved both the theory and the design. False positive analysis was refined over several decades, and new variants were developed to address practical system needs. So the main lesson from this survey is that Bloom filters are not just old data structures from 1970s. They are a family of related ideas that continue to evolve as both theoretical understanding and practical requirements improved. Overall, Bloom filters are a strong example of how theory and practice work together to shape data structured design. And these are the list of references I have used for my paper. Thank you for watching.